The competitor for delta H enthalpy is called entropy. So entropy is different than enthalpy, and entropy usually gets the symbol S. And spontaneity, predicting if a reaction will occur or not, is certainly something that entropy has a factor in. Now, entropy is really fascinating, and what entropy is all about, entropy is related to an increase in randomness. So instead of having ordered items, you end up with very random items. This entropy here is related to the matter dispersal we talked about earlier. We talked about how all reactions that are known are more likely to be energy dispersed or matter dispersed or both. Well, the energy dispersed is enthalpy, the matter dispersed part is entropy, and spontaneity is certainly related to an increase in the randomness in the matter dispersal. So we should talk about here what exactly entropy is all about. Clausius, there in the lower right-hand corner of the Clausius-Clapeyron equation. Anyway, he was the person that supposedly named entropy that after transformation, trope, I think is how you say it, I'm not sure. He thought that energy, i.e. enthalpy, was the giver of life, and entropy, on the other hand, is the taker away of life. Now, this is really antiquated, and I don't totally believe it. However, it's not totally wrong either, and we'll talk about wild entropy and what it means for society and how interesting it can actually be. So Boltzmann came up with this equation, S equals K natural log of W. And this is not an equation you need to know, but it's an equation I do want to talk about. And Boltzmann figured out that the entropy of the system equals K times the natural log of W, where W is the number of microstates of a system. K is a constant. It's the Boltzmann constant. You do not need to know / memorize it, but there's the value of it. And anyway, the important part here is that if you have fewer microstates, you won't have as high of an entropy. It'll be a lower entropy. But if you have a lot of microstates possible, then you'll have a higher entropy. And so entropy is a real interesting concept, but it is related to the number of microstates. And again, we're not going to use this equation ourselves per se, but I do want to talk about the origin of entropy, and this is where it all comes from. All spontaneous endothermic processes have an increase in entropy. So what that means is earlier we saw that ammonium nitrate solid dissolving in water and the temperature went down. That's endothermic. However, their solid did dissolve, so that's spontaneous. So what that means then is the entropy of that reaction was pretty big because that's what allowed the solid to dissolve in the water to make the solution and see the change of temperature, which ended up being colder. Here are some examples of the microstates. Let's look at the left-hand column first. All right. If you have one atom and there are two places to put it, you can figure out the number of microstates. And then to the right of the single atom system, you can imagine that that one atom could be in the left, which is the picture on the left, or that one atom could be on the right. So there are two microstates for one atom. All right. If you have two atoms in the same set of flasks, you could have those four different combinations. So for example, if you look there, by the way, here's the two atoms. You could have both of the atoms on the left side. That's what I just circled right there. You could have one atom on the left and one on the right. That would be a second microstate. You could flip the atoms, and that actually counts as a separate microstate. So B, instead of being on the right, would be on the left, etc. That's a third microstate. And you can even have a fourth microstate where they're both together, but in the opposite flask. So in this case, you have two atoms and four possible places they can go. And they figure this out mathematically, 2 squared, etc., etc. And then the next set of things is if you have three atoms, and I won't go through it, but there's actually 8 different possibilities that can happen with those 3 atoms. And as you have more and more and more atoms, you're just going to have a huge number of possible microstates. So you can see by the time you get to 10 atoms, you'll have 2 to the 10th or 1024 possible microstates. If you have Avogadro's number, you could calculate it at 2 times 6.0 0.022 times 10 to the 23rd, which is huge. Anyway, just realize, here's the punchline, the more atoms you have, the more entropy. All right, you're going to have different ways to orient them, and they're going to have more and more microstates. And more microstates means higher entropy. And this is what Boltzmann here kind of figured out. Now, again, we're not going to use microstates, but this is what it means to have an entropically favored system. More microstates, more entropy. And of course, the more atoms you have, that'll certainly be a big factor.
Molecular motions are much more random in the gas state than in either the liquid or solid states. Motion in a liquid is more random than that of a solid. Gases tend to have the highest entropies, while solids have the lowest.
Here's an example of a solid, a liquid, and a gas. And the entropy of a solid is usually less than the entropy of a liquid, and the liquids are definitely less, have a smaller entropy value than the gas. In that little table there on the right, you can see the actual entropy values, and we'll talk about that later. But solid there has a lower entropy than liquid. Liquid is less than gas. You can think about it that the solids have fewer microstates because they're more rigid. On the other hand, those gases are like all over the place. They can have a ton of microstates. So the punchline of this picture, all right, is when you're thinking about entropy, solids have less entropy than liquids, and liquids have less entropy than gases. And there is a way to quantify that. That's where those numbers come from. We'll talk about that here in a little bit. So which of these will have the highest entropy at 25 degrees Celsius? We'll see there's a temperature dependence, but they're all at the same temperature. That's kind of the idea. Anyway, here are the different possibilities. You've got iron, you've got water, mercury, xenon, and unobtainium, which is a silly reference from the first Avatar movie. Don't have to worry about that. That's just silly. Anyway, it's not so important here what the item is, but I would look at the state of matter. And you can see that xenon there is a gas. And gases always have higher entropy than liquids and solids. So if you have to pick the highest entropy and you don't have a table next to you, pick the gas, definitely.
Heptane at 1500 Kelvin has significantly greater molecular motion than it does at 200 Kelvin. The substance has greater entropy at 1500 Kelvin than at 200 Kelvin.
The entropy of a substance does get bigger as temperature goes up. And so in this example, we're looking at a compound called heptane, and the heptane entropy at the lower temperature is certainly less than the entropy of the heptane at the higher temperature. There's more movement, all right? They have more energy to move around, stuff like that. So if you have the same substance at two different temperatures, the higher temperature will have the higher entropy, and of course the lower temperature will have the lower entropy.
In general, the more complex a molecule, the greater its entropy. We can see this trend by comparing three alkane molecules. The amount of motion for each molecule translates into entropy. The more motion overall, the greater the entropy.
The larger the number of atoms in a molecule, the higher the entropy will be. So on the right-hand side, we see methane, ethane, and propane. They're all very similar. They're all tetrahedral carbon, sp3, etc., etc. However, methane has 1 carbon, ethane has 2, and propane has 3. And you can see the values there of the entropy, they're going up. So as the complexity, the more atoms in a molecule increases, the entropy will also increase. But this also applies just to molar mass. And on the left-hand side, you can see there's several of the noble gases, and we're going from helium up to xenon, and that follows the molar mass. So helium would be the smallest molar mass, and xenon at the bottom would be the highest molar mass. And entropy does go up as you have a bigger molar mass, and people feel it has to do with orienting the different electrons and stuff. That's kind of beyond where this class needs to go. But just realize that as molar mass goes up, you should have a higher entropy, or if you have more atoms, like you see on the right, that will have more entropy than if you have less atoms.
The entropy of a solid depends on the strength of the forces holding it together. The weaker the attractive forces, the greater the motion of the ions in the crystal lattice, and the greater the entropy.
We talked in Chem 222 about Coulomb's law and how as the number of positive and negative charges goes up, you have a stronger bond. Well, magnesium oxide is a positive 2, negative 2, and you can think about that as like a double handshake. The positive 2 of the magnesium is holding on to the negative 2 of the oxygen, and it's pretty tight. On the other hand, sodium fluoride, which is also ionic, by the way, is a positive 1, negative 1, like a single handshake, and it also holds on tightly, but not as tightly as magnesium oxide. So as the number of charges goes up, the entropy goes down. So magnesium oxide is lower than sodium fluoride. If you had, for example, aluminum nitride, ALN, you'd have a positive 3 aluminum and a negative 3 nitrogen. That would have probably even a smaller entropy than magnesium oxide does.
When potassium permanganate dissolves, its crystal lattice is broken apart, leading to an increase in disorder, and therefore an increase in entropy.
Usually, as you dissolve a solid in a solvent into a solution, usually the entropy is higher, all right? That's not all the time the case, but more often than not it isn't. So if you make a solution, that's usually entropy favored. Entropy likes having the solution over the pure solute and the pure solvent. So there are actually values of entropy available in problem set 1. And on the left-hand side there, this is an example of entropy values for different compounds. And our table that we're going to use is at the end of problem set 1 of Chem 223, or you can see it online. It's mhchem.org/thermo. And you'll see when you go to that website, there's an enthalpy delta H column, and there's also an entropy column. And for this discussion, look at the entropy values. But anyway, here entropy values you can see are always positive numbers. All right, there's no negatives and no zeros. We'll talk about that here in a little bit. And generally speaking, gases have higher entropies than liquids. The more complex a molecule it is, the higher the entropy will be. None of these numbers are things you have to know. Now, the only time you're going to have zero entropy is for pure elements in perfectly formed crystals at 0 Kelvin. And if you think about that, perfectly formed crystals is almost impossible to do. And we talked about crystal structures in Chem 222. It's difficult to make sometimes crystal structures, so that sounds unlikely. Pure elements, so no impurities, is also random, and 0 Kelvin is also very difficult to obtain. That's the only time you're going to have zero entropy, all right? This is what they call the third law of thermodynamics. And what the third law of thermodynamics essentially states is that the entropy values will always be greater than 0, all right? The only time you'll have 0 is for those perfectly formed elemental crystals, which is like never. So it's more than likely that you're going to have a positive value of thermodynamics.